So when we're talking about empirical formulas, we mean the smallest whole number ratio of elements in a compound. So each of these have a ratio of twice as many hydrogen atoms as carbon atoms, right? Do we see that relationship? This has twice as many hydrogen atoms as it has carbon atoms. So all of these three right here are called molecular formulas. These are called molecular formulas. And this right here, the smallest whole number ratio for that particular compound, is called its empirical formula. Okay, so these have to deal with really covalent compounds, not really ionic compounds. Okay, so on page 245, I want you to take a look at this example right here. Okay, we're going to walk through this example here under empirical formula, calculation of empirical formulas. Okay, so on page 245, it's walking us through how we calculate an empirical formula, and it's based off of a percent composition. Okay, so empirical formula and percent composition are related. They're going to help us calculate one and the other. Okay, so this says, assume we have 100 grams of a sample, and 78.1% of it is boron, and 21.9% of it is hydrogen. Okay, so we have some unknown compound here, and we have to decide what's the empirical formula, what's the relationship between these. The relationship could be BH, could be B2H, could be BH2, BH3. There's a ton of different combinations that we could have if we only have two elements that make up a compound. Does that make sense? We have a lot of different combinations that we could have as in terms of ratio of these elements. Okay, so we're going to take the percent composition they give us, and we're going to be able to calculate what this empirical formula is. What is the ratio between these two elements that give us our formula? Okay, so these are just examples. We could have lots of different combinations of formulas here. Okay, so what we're going to do is we're first going to just take these percents and we're going to convert them to grams. And when I say convert, I just mean literally put them into gram form. So we're going to take 78.1% and we're going to act like we have 78.1 grams of boron and 21.9 grams of hydrogen. Okay, so all we're doing is assuming that we're working with 100 grams of our substance. Okay, so we have 78.1%, which just means we're working with 78.1 grams of boron and 21.9 grams of hydrogen. Okay, so all we're doing here is saying instead of working with a percent, we're going to work with a gram substance, an amount of that substance. Does that make sense? So that's our first step for these empirical formula problems, is to convert your percents to grams. And when I say convert, I just mean literally put them into grams. Okay? Next, you're going to find out how many moles of each of these elements that you have. Okay, we want to find the number of moles of each of these elements. So we're going to convert grams of boron to moles, and we're going to convert grams of hydrogen to moles. Okay, so let's do boron first. Okay, when I want to convert from grams to moles, I'm going to start with my T-chart with what I know. If I want to convert from grams to moles, which needs to go on the bottom right here? Grams. And what goes on the top? Moles. Okay, and here the mole gets the 1. If we're going between moles and grams, moles gets the 1. And then what goes in this spot right here? The molar mass of boron, right? The molar mass of 1 mole of boron, and we get that directly from our periodic table. So I'm sorry, you will need your periodic table out today. So someone tell me what the molar mass of boron is. 10.81. 10.81. Boron is just a bead, okay, and it is atomic number 5. So now we're going to stop right there because we have moles of boron, which is what we want. We're done with grams. So we multiply across the whole top, divide by the whole bottom. So 78.1 divided by 10.81. Got our moles of boron, which is 7.22. So if we work with 78.1 grams, that means we have 7.22 moles of boron. Now we want to convert to moles of hydrogen. So we're going to take 21.9 grams of hydrogen, and we want to convert it to moles. Okay, so we've got 21.68 moles of hydrogen. Do we agree with both of our mole values? Okay, so now is where it takes a little extra step. We're going to look at the ratio between these two substances. We want to look at the ratio of moles, okay? Remember that when we have a formula, okay, if we have a formula like water, H2O, what's our ratio of hydrogen atoms to oxygen atoms? 2 to 1, right? Just if we were looking at moles of this substance, if I had a mole of water, how many moles of hydrogen would I have? How many moles of hydrogen would I have if I had 1 mole of water molecules? I would have 2 moles of hydrogen and 1 mole of oxygen. So that's our mole ratio here. So this is what we're going to do for boron and hydrogen. We're going to compare our mole ratios. And the way we do that is we're going to divide each of these numbers of moles by our smallest. Okay, so we're going to take the smallest number of moles we have, which is between these two, boron, right, 7.22. So we're going to divide this by 7.22 moles, and we get 1, right? We should always get a 1 somewhere. And we're going to divide hydrogen's mole value divided by the smallest, 7.22, to get a ratio. Okay, so what did we get when we took 21.68 divided by 7.22? Yeah, we get 3.00, which gives us a whole number ratio. That means our ratio of boron atoms to hydrogen atoms is 1 to 3. So we can put together our empirical formula to equal BH3. Okay, that means for this particular compound that is 78.1% boron and 21.9% hydrogen, it has this formula. Okay, so now the way you double check yourself here is to go ahead and calculate the percent composition. So I want you to calculate the percent composition of boron trihydride. Okay, boron trihydride. Calculate the percent composition of this particular molecule. We should get something very, very close to the percents that we started with. Maybe a decimal place off here or there just because of some rounding, but we should get something very close to what we started with. And this is just a way to double check yourself. Okay, so these are steps for solving empirical formulas. Okay, first of all, we should always start with a percent composition. Okay, usually it will give you a percent composition to start with. Okay, if it doesn't, that's fine. But if it does, we start with, then we convert that percent to grams. So we're going to change percents to grams. And all that means here is that if it was 75%, that means it's 75 grams. Okay, we assume that we're working with 100 total grams of our substance. So if it's 75%, that means we want 75 grams. Okay, our next step is to convert each element from grams to moles. Convert each element from grams to moles. Okay. Next, we'll divide each amount of moles by the smallest. Okay, and I'll put in there smallest amount of moles, just as a reminder. Okay, divide each amount of moles by the smallest amount of moles you had out of all of those elements. So here, this last step right here should give you your ratios, right? One should come out as a 1 because you've got the smallest amount. So if you divide the smallest by the smallest, you should get a 1. The rest of them should give you whole numbers, hopefully. And we're gonna see what it takes if it doesn't give you a whole number. But they should give you whole numbers or close to that. Okay, but those are going to give you the ratios. So once you have your ratios, then you can build your compound. Okay, so once you have your ratios together, then you can build your compound. Okay? Okay, so this practice we're going to do together in class, 89.14% gold and 10.8% oxygen. Okay? So first and foremost, we're going to put those percents into grams. Okay, and right from there we can go ahead so you can go ahead and start converting to moles of each of these as I rewrite. Our molar mass of gold from the periodic table comes out to be 196.97. Okay, so what do we get for moles of gold? Isabel, why don't you tell me what you got for moles of gold only? 0.45 moles. Okay, do we agree? For gold? Okay, Danny, why don't you tell me what you got for moles of oxygen? 1.175. Yeah? Okay. Okay, so our moles of oxygen should be 0.675. Okay, so now we've got both of our moles. What's our next step? Divide by the smallest number of moles. So which is our smaller number of moles here? Gold or oxygen? Gold. So we're going to divide each of these by 0.45. And I'm going to have to move my work down here. So if we take 0.45 moles of AU divided by 0.45, we get 1. And if we take 0.675 divided by 0.45, we get a value of 1.5. So here, do we have a whole number? No. Okay, we don't really have one even really close enough to round to. Okay, if it's 0.97, 0.03, 0.04, if it's that close, we can round to a whole number, but here we are smack in the middle. Okay, so if I build my compound right now, it looks like this. AuO 1.5. Does that work? No. No. It does not work. Okay? So what's our step going to have to be here? Multiply by 2. We doubled the whole compound. Okay, so we're going to double the whole compound here, which means we would be left with AU2O3. We have to double both atoms. We cannot just double the one with the uneven or the mixed number subscript. We double both of them. Okay, so now you can check yourself by finding the percent composition of AU2O3. Okay, so that could be a quick check for you to check that empirical formula. So if we want to find the percent composition of AU2O3 or gold oxide, we would take its molar mass and we'd divide one of those elements by the total. Okay, just to check ourselves. Okay, so why don't we go ahead and do that? Okay, so I got 10.86% oxygen, pretty close to the 10.8 that we started with, which means we are good to go. Okay, so here's, if I want to check my percent composition, just to make sure that I am on the right path. Does everyone understand the double that we did? Okay, and understand why we have to double both elements? We can't just double one. That would have changed our percent composition, would have changed our ratio. Okay, because our ratio should be 1 gold to 1.5 oxygens. Okay, which is what this ratio is right here. Okay? All right, let's try the next one. Okay, 4 elements to deal with. So hopefully I left you enough room. You might have to write pretty small. Okay, but we've got 4 things we're working with here. No, I'm sorry. Oh, yeah, 4 things. Okay, so 21.2 grams of nitrogen, 6.1 grams of hydrogen, 24.2 grams of sulfur, and 48.5 grams of oxygen. Okay, so those percents can just be put into grams, right? We don't have to do anything crazy for that, but we do now need to start calculating moles for each of these. Yeah. Our next step now, once we have all our moles, is to divide by the smallest. So which of these elements gives me the smallest number of moles? Sulfur, right? Or 0.755. Okay? So now I'm going to take each of my mole values divided by 0.755. So when we do these ratios, we should always come out with a 1, right? Something should always come out as a 1. So we can't reduce these any farther, okay, because something is already a 1. We can't reduce it any past that. Okay, so then we just start building our compound basically in the order of elements they give to us. Okay, because sometimes the order gets a little bit tricky. You don't know which should go first, which should go second. Typically, it can go in the order they give to you. Okay, so in that case, our element or our compound would be N2H8SO4. Okay. Okay, so when you write your answer, you're not just giving me the final ratios. You're giving me this compound, this empirical formula, a chemical formula. Okay? Good question. So your final answer here is N2H8SO4. Okay? To find the percent composition of this, since we don't know its formula, basically what we're going to do is add up all of these grams to find the total amount of substance we're working with.
Do we have to add it up since it tells us it's 140 grams?
It tells us it's 140 grams. So no, you don't have to add it up since it tells you the total. Sorry. Okay? It tells us that our whole sample is 140 grams, and we want to find the percent composition of that substance. So percent composition of hydrogen within this compound, we would take 2.24 grams divided by 140, since that's our total. And that gives us the percent of hydrogen in this particular compound. Make sure that once you get it in a decimal form, you convert it to a percent, which is 1.6%. And make sure you include your hydrogen label in there so you know what element you're working with. Okay. Then we move on to nitrogen. And our oxygen. Okay, so now that we've got them all in percents, you should be able to do the rest. Okay, so I want you to take this by yourself and finish this one up. Since we've got them all in percents already, you should know how to do the rest of it. Okay, it comes with, it ends up being HNO3. Okay, so when I ask you to name this, if your H comes first, that's a big clue that it's an acid, right? That's your clue. And then you look at this anion right here. NO3 minus 1 is what anion? Nitrate, which means you name it nitric acid. Ratio. So we talked about the difference between an empirical formula that looked like this and a molecular formula that looked like this, CH4 or C3H6 or C4H8. These are all molecular formulas. This is its empirical formula. Okay, its empirical formula is the smallest ratio. Molecular formulas could be larger versions of that compound. Okay, doesn't mean they're the same compound. They're not. They act differently, but it's just a bigger version of that. Okay?
Why don't you have the oxygen in there?
Oh, this. Sorry, I wasn't particularly looking at this compound. I didn't mean to make it coincide with that word. That's not what I was doing. Sorry. I was just looking at the example from the beginning of class that we talked about. Okay. So what we're going to do now is we're going to be able to compare empirical formulas and molecular formulas, and we're going to compare those two. So what we're going to do here is now we're going to take a look at this practice problem up here. Okay? So it says empirical formula of a substance is CH2O. Molar mass of its molecular formula, which could be a bigger version, could be the empirical formula, they could be the same thing, is 180 grams per mole. What is its molecular formula? Okay, so here, someone already did all the work for you of finding the empirical formula. Okay, someone did that work for you, which is CH2O. Okay, so once we have the empirical formula, we want to find the molar mass. So find molar mass of empirical formula. Okay, that's the first step there. So someone did all the work of the empirical formula for you. So we want to find molar mass of this empirical formula. So we're going to take 1 carbon plus 2 hydrogens plus 1 oxygen. Okay, and if we keep these simplistic here as whole numbers, because all of these round to whole numbers pretty much, we get about 30 grams per mole. Depending on decimals you use, you might get a little bit higher, and that's okay. But we get essentially a molar mass of 30 grams per mole. Do we agree?
Yep.
So now we want to look at basically the ratio between the empirical formula and the molecular formula. Okay? What's say the molar mass of the molecular formula is?
180.
180. So we're going to find out how many of these compounds can fit into that 180 gram per mole molecule. So we're going to take now the molecular divided by the empirical formula. Molecular molar mass divided by empirical molar mass. And we get a molecular formula that's 6 times what the empirical formula is. Okay, it's 6 times as large. Which means we're going to take 6 times CH2O, and we get an we get a molecular formula that looks like this: C6H12O6. In our molecular formula, our ratios are still the same. It's still a 1 to 2 to 1 ratio, but it's a much bigger version. Okay, and the way we can tell the difference between those is the molar masses. Okay, so in this particular problem, someone did the work to find the empirical formula for you, but its molecular formula happened to be much bigger, okay, of this unknown compound. Could the molecular formula and the empirical formula be the same?
Yeah.
Yeah, they could be the same. Okay, but molecular formula will always be the same or larger than. Okay, always divide the molecular molar mass by the empirical formula molar mass. So if you need to make a note about that on your practice sheet or in your notes, go ahead and do that. Okay, you would take the molecular molar mass divided by the empirical molar mass. Okay, molecular divided by empirical. Okay, then once you have your whole answer, your whole number answer here, you're going to distribute that throughout the empirical formula. Okay? Questions? Let's try this last problem on your worksheet now together. And in this one, they didn't do the work of finding the empirical formula for you, so you have to do that work. You have to find the empirical formula, and from there we can find the molecular formula. And this one didn't even start in percents. So what's the first thing you have to do here? You got to find percents first, and then you can change back to grams. So these problems take a little bit of work, okay? You have to start with a percent composition. Must start with a percent composition. Okay, so if you're following along or if you're stuck, once you have your mole values here for your empirical formula, you should divide by the smallest number of moles. Okay, which means we get an empirical formula of CH3O. What's the molar mass of CH3O? 31? 31 grams per mole. Okay, so if we have a molecular molar mass, or molecular formula molar mass of 62 grams per mole, and an empirical molar mass of 31 grams per mole, that means the ratio between the empirical formula and the molecular formula is 2. So we distribute that 2 to the empirical formula, which leaves us with a molecular formula of C2H6O2.